All right. So today we have Valdo Tatitscheff, who will talk about global variance of n equals to 1 star theories and Calogero Moser systems. Take it away.
Thanks a lot. Thanks a lot for the invitation. So indeed, I'm going to discuss some recent results in collaboration with Jeremias Aguilera Damia, Ricardo Agurio, Antoine Bourget, and Romain Van de Populier concerning the relationship between n equals 1 star theories and Calogero Moser systems. So I'm gonna start with a very general introductory slide to tell you that this study fits within the general field of the relation between supersymmetric gauge theories and integrable systems. And particularly the correspondence that we're interested in is that between 4D n equals 2 gauge theories and complex integrable systems as it arises in the context of Seiberg-Witten theory. So a large class of complex integrable systems is that of Hitchin systems, which are all realized as the Seiberg-Witten integrable systems corresponding to theories in class S. And there has been a very rich interplay in the past and still today between the study of Hitchin systems and theories in class S. So in this talk, instead of studying this correspondence in all generality, we will focus on a specific class of integrable systems, namely elliptic Calogero Moser integrable systems. And the goal of the talk is to explain how the natural notion of global variant from four-dimensional gauge theories transposes in an interesting way to complex integrable systems.
I have a question already,
Sure.
because you say that every Hitchin system is realized as a class S system. Is this kind of obvious by definition, or is this something one has to prove?
I mean, to me, it follows from the definition of a
Definition. Okay. All right. Okay. Good.
Yeah,
Thanks.
I mean, it's a subtle correspondence. So there might be, you have to define Hitchin systems precisely and
Okay, I see.
accordingly. But I would say that the definition of theories in class S is that they are the 4D n equals 2 theories for which the Seiberg-Witten integrable system is a Hitchin system.
Okay. All right. Good. All right. Thanks.
All right. So the outline of the talk is the following. I will start reviewing some aspects of the notion of global variance of four-dimensional gauge theories. Then we will discuss n equals 1 theories and their massive vacua. Third, we will study elliptic Calogero Moser systems. And last, I will present the notion we introduced, namely that of global variance of Calogero Moser systems. Okay, so let's start with the global variance of four-dimensional theories. So the law is that to specify a Yang-Mills theory in 4 dimensions, let me just try to move this. Very good. So to specify a Yang-Mills theory in 4 dimensions, in general, it's not enough to give just the field content and the Lagrangian density of the theory. So for example, if you consider the pure Yang-Mills Lagrangian in 4 dimensions, which is written here, it doesn't distinguish SUN, PSUN, or any intermediate SUN mod ZK, where K divides N, Yang-Mills theories. Instead, these theories, they're distinguished by their spectrum of genuine line operators, and this is what a global variant encodes. So as line operators, we know, because we're studying a Yang-Mills theory, that we have Wilson lines, which are labeled by electric charges, namely representations of the gauge algebra G, or equivalently points in the weight lattice of the gauge algebra modulo the Weil group. We also have Hooft lines, which are labeled by representations of the magnetic dual group, G dual, algebra, sorry, or equivalently by points in the co-weight lattice modulo the Weil group. And more generally, we have dionic lines, Hooft-Wilson lines, which correspond to points in the product of the co-weight lattice and the weight lattice modulo the Weil group. So this was proved by Kapustin in 2005. Now we also have a natural pairing, which is invariant under the Weil group between the co-weight lattice and the weight lattice, which is rational valued. And this pairing descends to a pairing which is antisymmetric and non-degenerate. So an antisymmetric non-degenerate pairing between the quotient of the weight lattice by the root lattice and the co-weight lattice by the co-root lattice. Which is encoding the standard notion of anality for representations in the case of SUN. With this pairing, we can define an antisymmetric non-degenerate bilinear forms on equivalence classes of Wilson-Tooth lines. And this is the pairing that appears in the Dirac-Schwinger-Zwanziger quantization condition, which is that in order for the theory to be consistent, any two genuine Wilson-Tooth lines, L1 and L2, must be such that their pairing is integer instead of being rational. Now, this notion allows us to define that of global variant of a four-dimensional theory. So a global variant is a choice of a maximal collection of mutually local Wilson-Tooth line operators. And we have two equivalent redefinitions of this notion of global variant. The first one is that a global variant is a maximal sublattice of Wilson-Tooth lines integral with respect to the pairing that we defined in the previous slide, or equivalently, that a global variant is a subgroup of the quotient of the co-weight lattice by the co-root lattice times the weight lattice modulo the root lattice, which is Lagrangian with respect to our non-degenerate anti-symmetric bilinear form. So the simplest example is that of the Lie algebra SU2, for which the quotients co-weight modulo co-roots and weights modulo roots is isomorphic to Z2. And the pairing is the one expressed here. And when we study the global variance of SU2 Yang-Mills theories, we find three possible global variants, which are judiciously called SU2, SO3 plus, and SO3 minus. So the SU2 global variant has all possible Wilson lines and only tooth lines in adjoint representations, or more generally in representations of NLT 0 of in the case of SU2, n is 2, so 2 LET 0. The global variant SO3 plus is characterized by the fact that it has Wilson lines only in representations of NLET 0 and all possible tooth lines. And the global variant SO3 minus has no elementary fundamental Wilson lines and no fundamental tooth lines, but a dionic line which plays the role of the fundamental line, genuine line in this theory. So I just want to mention that for general theories in class S and of type A1, it's known that half BPS line operators are in bijective correspondence with integral laminations, which are specific geometric objects on surfaces. And in that case, the Dirac-Schwinger-Zwanziger pairing is related to the intersection pairing, which is a well-defined geometric quantity that we can define for pairs of laminations. Very good. So the notion of global variance is interesting in particular because it leads to a refinement of the standard notion of electric-magnetic duality. So when the gauge algebra is simply laced, the duality group of n equals 4 Yang-Mills theories is PSL2Z. PSL2Z is generated by the standard elements S and T. S acts as the standard electric-magnetic duality, so it sends a tooth line of charge M, magnetic charge M, electric charge E, to a Wilson tooth line of charge E minus M, whereas T corresponds to a 2-pi shift of theta, and according to the Witten effect, T also shuffles line operators by sending a line operator of charge ME to a line operator of charge ME plus M. Okay, so three remarks. The first is that some global variants, as defined before, are naturally associated to compact connected Lie groups, such that their Lie algebra is the gauge algebra we started with. And in that case, the global variance is just given by the product of the co-character lattice gamma G of the group and the character lattice lambda G of the group. So this is the case, for example, in the examples that we showed before for the SU2 and the SO3 plus global variance, but not for the SO3 minus global variant. And in that sense, the notion of global variant is a generalization of the set of Lie groups associated to a given compact Lie algebra. The second remark is that, contrarily to the duality graph that you have on the right of the slide here, which is connected, so this is for the Lie algebra SU2, when n has squared prime factors, we find that the duality graphs are not connected. So I just want to emphasize that the duality graphs relating the global variance given a fixed Lie algebra is not necessarily connected. And then continuing the remark of before, for general theories in class S, in the case of general theories in class S of type A1, the group PSL2Z, the duality group, is replaced by the mapping class group of the UV curve, and it acts on laminations in a natural way. Okay, maybe do you have questions at this point? Okay, very good. So let me now move to the second topic, namely n equals 1 star theories and the classification of their massive vacua. So a convenient way to define n equals 1 star theories with gauge algebra G is to say that they are mass deformations of n equals 4 G supreme Mills theories. So in some sense, these n equals 1 gauge theories are distinguished by the fact that they originate from n equals 4 supreme Mills, and they inherit a lot of the very nice properties of n equals 4 supreme Mills, hence the notation n equals 1 star. So they emit a nice perturbative description. In n equals 1 language, their matter content is one vector superfield and three massive adjoint chiral superfields, phi I. And the superpotential, as I said, is just obtained from that of n equals 4 super-Young Mills by adding mass terms for the massive adjoint chiral superfields. And if we do that in a way which is generic enough, then we obtain n equals 1 star theory. So we can rescale the chiral superfields phi I to define this x, y, and z, and we can rewrite the superpotential as shown on the right of this equation here. Now, as usual, for a 4D n equals 1 theory, we can define the notion of classical modular space of vacua. It's the quotient of the space of solutions to F terms and D terms by the action of the gauge group, or equivalently, it's the quotient of the space of solutions to F terms by the adjoint action of the complexified gauge group or algebra. And with the superpotential rewritten as on the right-hand side of this equation here, the space of solution to F terms takes a very nice form because it's just given by the triplets of elements X, Y, and Z in the complexified gauge algebra, which satisfy these equations that X should be equal to the commutator of Y and Z, and two similar equations obtained by cyclic permutations. This is exactly the notion of SL2 triple in Lie algebras, which is a topic that has been studied a lot in the context of Lie theory. Therefore, we can say that the semi-classical vacua of n equals 1 star theories are in one-to-one correspondence with orbits of SL2 triples in the complexified gauge algebra. This being said, we can also describe very nicely the unbroken gauge algebra given such a choice of SL2 triple, which again corresponds to a solution to the F terms modulo the action of the complexified gauge algebra. In that case, the unbroken gauge algebra is just the centralizer of the SL2 triple X, Y, Z. Now, if we fix such an SL2 triple, so equivalently a classical vacuum of the theory, then the dynamics reduces to that of pure n equals 1 G unbroken super-Young Mills, where G unbroken is this centralizer sub-algebra of G. Now, of course, when we say that we have pure super-Young Mills corresponding to some Lie algebra, we also have to specify the global variance. This is subtle, and this is a big part of the work that we have been doing in this paper. And the precise global variant, of course, depends on that of the UV n equals 1 star theory. Now let's consider a specific example. So namely the case where G is SUN, and let's discuss the massive vacua of n equals 1 star SUN theories. So as explained, in order to classify the vacua, we have to look at the orbits of SL2 triples in the complexified gauge algebra, which in that case is SLNC. And equivalently, this corresponds to the nilpotent orbits in SLNC, which is a classical result in Lie theory. Or equivalently again, it corresponds bijectively to the partitions of n, where a partition of n is a way to write n as a sum of positive integers, n equals lambda 1 plus lambda 1 plus lambda 1 mu 1 times, plus mu 2 times lambda 2, etc., plus mu k times lambda k, where we can order the lambda I saying that lambda 1 is strictly bigger than lambda 2, etc., etc. And for all I, lambda I and mu I are taken to be positive integers. Now we have a powerful result from the theory of nilpotent orbits in mathematics, which is the Springer-Steinberg theorem, telling us the structure of the unbroken gauge algebra in a generic case. Like we fix a partition, meaning that we fix again a vacuum, a classical vacuum for an equals 1 star theory. And we know that the unbroken gauge algebra is so we have the S and then a direct sum of unitary gauge algebras. So we have a general formula. So let's consider two very explicit cases to fix ideas, namely the case of SU3 and SU4. So on the left column, you have the case of SU3. And we have to look at partitions of 3 in order to understand the classification of vacua of n equals 1 star SU3 theory. So we have 3 possible partitions of 3. The first one is 3 equals 3. It's just writing 3 as itself. In that case, the result on the structure of the unbroken gauge algebra tells us that the unbroken gauge algebra is trivial. Then we have the partition 3 equals 2 plus 1. And we find that the unbroken gauge algebra is U1. And last, we have the partition 3 equals 1 plus 1 plus 1, in which case we find that the unbroken gauge algebra is SU3. So, for example, if we consider the last partition, it corresponds to a classical vacuum of the theory. And we know that the dynamics reduces at intermediate energy scales to that of pure some global variant of SU3 superyoung mills. Now, for an example of a slightly bigger complexity, you can consider SU4. Again, we have the partition 4 equals 4. The unbroken gauge algebra is trivial. We have the partition 4 equals 3 plus 1, where the unbroken gauge algebra is U1, etc., etc. So we are interested in massive vacua and not all vacua, and we want to avoid at all costs the abelian gauge factors in G unbroken, because if we find an abelian factor in the unbroken gauge algebra, then the vacua of this theory are not going to be massive, but they're going to be instead gapless. However, in contrast, when we consider pure n equals 1 superyoung mills with a simple gauge algebra G prime on R4, we know that it confines with a mass gap. And so that gives us a very natural way to obtain massive vacua. In order to obtain massive vacua, we will then restrict to partitions of the form lambda equals mu times lambda. So with only one factor of lambda, so k equals 1 in the definition of partitions above. And if we do that, by the Springer-Steinberg theorem, we will avoid the presence of abelian factors in the unbroken gauge algebra. And so we know that we will obtain massive vacua by doing that. Do you have questions on this strategy to classify the vacua of n equals 1 star theories, the definition of n equals 1 star theories? Very good. Okay, so let's now turn to the study of n equals 1 star theories on R3 times S1, because it's in this setup that the correspondence with Calogero Moser systems is going to be the cleanest. And let me start by a remark to explain the main difference with respect to studying this n equals 1 star theories on R4. So on R4, if we consider pure superyoung mills, the number of vacua of pure n equals 1 G prime superyoung mills for some Lie group G prime only depends on the Lie algebra of G prime. However, there are subtle properties that depend on the global variance. Typically, the low energy effective theory in the vacua of n equals 1 G prime superyoung mills depend on the precise global variant that we're considering. So a standard and simple example, again, in the case n equals 3, is that if we take pure n equals 1 SU3 superyoung mills, then it has 3 trivially gapped vacua. So H dual here is the dual Coxeter number. This is a general result. We could replace G by some other gauge group. Whereas if we consider pure n equals 1 PSU3 superyoung mills, for any global variant corresponding to the group PSU3s, there are 3 of them, then in every case, we find 2 trivially gapped vacua and 1 vacuum which hosts a discrete Z3 gauge theory. Now let's study what's going on when we compactify the theory, when we consider the theory on R3 times S1. So if we consider a 4-dimensional discrete ZK gauge theory on R3 times S1, then we find that it admits K distinct gap vacua, which follow from the fact that we can turn on Wilson lines for this discrete gauge symmetry. Therefore, if we come back to the example of pure superior Mills above, the count of gap vacua for these theories on R3 times S1 depends on the global variant. For example, in the pure SU3 case, we will find 3 massive vacua on R3 times S1, whereas in the case of PSU3 superior Mills, we will find 5 vacua on R3 times S1, 2 coming from the 2 trivially gapped vacua, and 3 vacua coming from the unique vacua hosting a discrete Z3 gauge theory on R4. So this is these 2 tables here. I mean, what I just said fits within these 2 tables. So these 2 tables correspond to the cases of n equals 1 star theories. So we factor in the classification of vacua, of massive vacua that we explained before, as well as this multiplication of vacua that arises when we consider the theory on R3 times S1 instead of considering it on R4. So in the case of SU3 n equals 1 star, in the partition 3 equals 3, we found that the unbroken gauge algebra was trivial, but then here we want to really focus on the specific unbroken gauge group. And in that case, the unbroken gauge group is the discrete group Z3. And this leads to 3 massive vacua on R3 times S1. Whereas if we consider the partition 3 equals 1 plus 1 plus 1, then the unbroken gauge group is SU3. And we again find 3 massive vacua on R3 times S1. Now, if we move to some global variant corresponding to the group PSU3 for the n equals 1 star theory, so we have the same 2 partitions leading to massive vacua. The partition 3 equals 3 gives us a trivial unbroken gauge group, and this leads to 1 massive vacua on R3 times S1. Whereas in the partition 3 equals 1 plus 1 plus 1, the unbroken gauge group is PSU3, and as we just said, this PSU3 n equals 1 super Mills admits 5 massive vacua on R3 times S1. So we find that in both cases, the theories admit the same number of vacua on R3 times S1, namely 6 vacua, but they do not arise in the same way. The fact that these 2 theories admit the same number of vacua on R3 times S1 is a good thing because we know that they are secretly related by sequences of dualities, like sequences of S and T's, so they must have the same number of massive vacua on R3 times S1. But the fact that they do not arise in the same way is an important point that will play an important role in what follows. So remember this thing that all the SU3 n equals 1 star theories admit 6 vacua on R3 times S1 because it's going to be relevant later on.
So one question, if it's all right.
Yep, sure.
So, but it's not always the case that you have the same number of massive vacua, but just sourced differently, or it's always like that?
No, so that was the next remark. It can be worse. So that's connected to the remark I was making about the fact that the duality graph for those global variants is not necessarily connected. If you have a connected duality graph, then again, because you have duality, you know that all of the theories belonging to the same connected component of the duality graph must have the same number of vacua on R3 times S1. But if you have different connected components, so the simplest case is for SU4 theories, then you can have different numbers of vacua. And typically, if you take SU4 n equals 1 star theory, it has 12 massive vacua on R3 times S1, whereas the global variant SU4 mod Z2 not has 16 massive vacua on R3 times S1. So it doesn't have to be the same number. But you know that if the theories are related by duality, then they must have the same number of massive vacua on R3 times S1.
That's it. Thank you.
Can you explain this difference by gauging some one-form symmetry?
Yeah, definitely. So
You see it from there? Mm-hmm.
yes, yeah. Even though it might be subtle, but yes, in principle you can. I'm confident that you can. So a word of caution that everything we said until now was relying on a perturbative description of n equals 1 star theories. So we have the UV gauge coupling, and we are following the dynamics of the theory starting from the UV gauge coupling, and then we have the spontaneous breakdown of the gauge group, and then we end up in a vacuum in which we have an effective dynamics, which is that of pure super-Young Mills, which confines, etc. But of course, all of the reasoning can be trusted only when the theory stays weakly coupled all along the RG flow. So when we start from a very large value of the gauge coupling, then there is no hope that we can trust the perturbative description we just did. And that's where the n equals 2 star or n equals 4 origin of n equals 1 star theories save the day, because we have Seiberg-Witten theory, which is non-perturbative. So we can say things about the non-perturbative dynamics of these theories. And that's exactly where the correspondence with twisted elliptic Calogero Moser systems arise. So that's what I want to discuss now. Further questions before we move to twisted elliptic Calogero Moser systems? Right. Okay. So there's going to be a bit of a jump here in terms of topics. Like the topic will look completely different at first, but then don't worry, like we will connect that as much as possible to n equals 1 star theories. So elliptic Calogero Moser systems are canonical or remarkable instances of integrable systems of interacting particles in one dimension. So in our case, it's going to be one complex dimension, but it's a family of integrable systems that was first derived in the 70s and the 80s. And again, today it's really standing out as a very remarkable theory of such integrable systems, which has a very interesting property, is that the interaction potential is related to Lie algebraic data, as I will explain. So let's consider a finite dimensional complex simple Lie algebra, GC, which we take to be of rank n. And we set just HC to be its Cartan subalgebra, the root system delta of GC, and delta of GC plus the subset of positive roots. And then as before, we denote lambda R the root lattice of GC, lambda weight the weight lattice of GC, gamma R the co-root lattice, and gamma W the co-weight lattice. So we can now define the elliptic Calogero Moser system corresponding to this Lie algebra GC. So it is the system of n interacting particles on a torus, so on some elliptic curve E tau, with pairwise repulsive interactions, namely the interaction potential for this dynamical system is given by this sum of Weierstrass P functions. So the potential is 1/2 of the sum over all roots in the complex Lie algebra GC of P of alpha Z tau, where Z is a lift of the vector of positions of the particle on the torus. So the positions of the torus have denoted them Z1, Zn. So this forms a vector small z of periodic variables. And I take a lift of that to Cn. And I identify Cn with the Cartan subalgebra of GC. And that gives me something that I can pair in a very natural way with roots of the Lie algebra. And that's exactly how we define the interaction potential for elliptic Calogero Moser systems. So a couple of remarks again. So this potential is independent of the choice of lift, which is a good thing. This comes from the fact that P is an elliptic function. So that's why we can say that the elliptic Calogero Moser system is a dynamical systems of particle on a torus and not in the complex plane. Second remark is that for GC of type AN, instead of taking n particles on the torus, we can take n plus 1 particles on the torus, which satisfy a constraint, namely that the sum of Zi is 0. So this gets along well with the standard representation of the root systems of type A. And typically, like in the case of SL3C, so root system of type A2, the interaction potential is going to be the sum of P Z1 minus Z2, P Z1 minus Z3, and P Z2 minus Z3, which corresponds to the 3 positive roots of the Lie algebra. And the third remark is that this interaction potential is naturally invariant under the action of the Weil group on this vector of position of our particles, either the lift to Cn or the vector of positions on the elliptic curve. And more generally, we can see that the interaction potential is actually invariant under all the symmetries of the root system that we are considering. So there are some subtleties, for example, in type D, that the Weyl group is not exactly the same thing as the set of symmetries of the root system. And so that's why I want to make this remark. Okay, and so part of the law concerning these Calogero-Moser systems is that whatever the choice of finite dimensional complex simple algebra we are making, this elliptic Calogero-Moser system, the system defined in this way, is a completely integrable complex dynamical system. Maybe questions about these elliptic Calogero-Moser systems? No questions, very good. So let's consider the specific example of SL3 a bit more precisely, like with drawing. So I've rewritten the potential, the interaction potential of the SL3 Calogero-Moser system. So we take, as I said, the representation in which we take 3 particles on the torus and not only 2. So the rank is 2. But we take 3 particles that satisfy this constraint that Z1 plus Z2 plus Z3 is equal to 0. So on the left of the figure, you have an example of a configuration of points in the complex plane that satisfy this constraint. And when we project it on the torus, we get 3 points on the torus, Z1, Z2, Z3, which we interpret as the particles that are the dynamical variables of our integrable system. And then on the right of this figure, you have the root system of type A2 with the positive roots lambda1 minus lambda2, lambda1 minus lambda3, and lambda2 minus lambda3, which appear in the interaction potential above. Now I want to discuss a bit more the symmetries of the interaction potential. So let's consider the fundamental co-weights of SL3C. So in the standard representation of SL3C, the fundamental co-weights are these matrices Chi1 and Chi2. And again, because of the periodicity properties of the Weierstrass P functions, we see that if we shift the vector of positions Z1, Z2, Z3, either horizontally, by that I mean sending Z1, Z2, Z3 to Z1, Z2, Z3 plus Chi1, or vertically, meaning that I will shift by Chi1 times tau, then the potential is invariant. So that's what I want to say when saying that the potential is invariant under horizontal and vertical shifts of the position vector by co-weights. Now, in fact, in order to match Calogero-Moser systems with physics, we need a slightly more general notion of elliptic Calogero-Moser system, which is that of twisted elliptic Calogero-Moser systems. So instead of looking at the Weierstrass P function, we consider so on top of the Weierstrass P function, we'll consider the so-called n-twisted Weierstrass P function, which is obtained by summing the Weierstrass P function along nth period of the torus, defined in this way. So this n-twisted Weierstrass P function has improved periodicities, like it's periodic of period 1 in the vertical direction, which is to say that Pn alpha is the same as Pn alpha plus tau, and it has periodicity 1 over n in the horizontal direction. That is to say that Pn of alpha is the same as Pn of alpha plus 1 over n. Now we can define the twisted elliptic Calogero-Moser system. So when GC is non-simply laced, we take n equals 2 for the root system of type B, C, and F4, which is because we have a double edge in the Dynkin diagram, and n equals 3 for G2 because we have a triple edge in the Dynkin diagram. And then we define the interaction potential of the twisted elliptic Calogero-Moser system to be the sum as before over the roots of the Lie algebra, except that we split in 2 sums, one over the long roots of the Lie algebra and one over the short roots of the Lie algebra. So it turns out that this definition also defines a complex, completely integrable system. Now we can also generalize this definition when GC is simply laced, simply by saying that the twisted elliptic Calogero-Moser potential coincides with the elliptic Calogero-Moser potential that we defined before. Now, with this definition, for all complex simple Lie algebra GC, the twisted Calogero-Moser potential is invariant under horizontal shifts by weights and vertical shifts by co-weights. And these symmetries, as we will see in the next slide, are very natural from the perspective of supersymmetric gauge theories. And in fact, indeed, it's the twisted variants of elliptic Calogero-Moser systems which appears as the Seiberg-Witten integrable systems corresponding to n equals 2 star theories instead of the standard notion of elliptic Calogero-Moser system. Questions?
Maybe let me ask one question that I think maybe we discussed already. So you put the coupling constants to be the same, or rather one is GL and the other one is GL divided by N. So
yes.
Can you say something about the case where this would not be related? There would be two different coupling constants. Is this related to some theory?
I don't remember on the spot. I'm sorry. Yeah.
I also don't remember.
So what was the reason? I think so. I hope it's not bullshit, but I think the reason is that if you don't fix the coefficients like that, then you're losing some of the duality properties when you're looking at the electric magnetic duality of these Calogero-Moser systems. But I might be wrong. I don't remember.
Yeah. That's for sure. And the question was, if you don't put them equal, do you get some other n equal 2 theory or what's?
That's a very good question. I don't know.
Yeah. And maybe one thing then it's rather a comment than a question, but just for a clarification that indeed the twisted system, it appears that it's let's say for people who are interested only in A type, so for SUN, so the previous slide, it would seem that it's useless to introduce this thing. And just to insist that in these periodicities that you mentioned at the end of this slide, this is really the essential thing. And so even for A type, it will be super important. And maybe that's, I guess that's what you would say later. But
Indeed.
maybe some people are wondering, okay, I will ignore the non-simply laced, but you cannot ignore it.
Yes.
I have to admit, I was willing to ignore the non-simply laced.
Exactly. I'm speaking for you. I'm mostly speaking for you.
Thank you very much. Okay, so let's take this very serious.
Thanks. No, so when the Lie algebra is simply laced, then there is something Lie theoretic happening, which might seem like a technicality, which is the fact that under the isomorphism between H and H dual, where H is the Cartan subalgebra, provided by the Killing form, the weight lattice is mapped to the co-weight lattice. This is not the case for non-simply laced algebras. And indeed, so for non-simply laced algebras, it is mandatory to consider the twisted elliptic Calogero-Moser system. And it turns out that the philosophy, like thinking to elliptic Calogero-Moser systems, with this philosophy of twisted elliptic Calogero-Moser systems, makes a lot of things much more natural. So I think indeed the good philosophy is to remember that we want an integrable system with horizontal symmetries corresponding to weights and vertical symmetries corresponding to co-weights. That is the main lesson from twisted elliptic Calogero-Moser systems. All right. So Calogero-Moser systems are Seiberg-Witten systems. So this is a fact that I will not develop a lot, but which is known since, I don't know, 25 years. That's the twisted elliptic Calogero-Moser system corresponding to the gauge algebra, the complexified gauge algebra GC, is the Seiberg-Witten integrable system corresponding to some n equals 2 star theory with gauge algebra G. So I'm writing relative here because the whole point of this talk and our paper is to define what the good notion of twisted elliptic Calogero-Moser system is when we start caring about the notion of global variant for n equals 2 star and n equals 1 star theories. So the correspondent goes by identifying the phase space of the twisted elliptic Calogero-Moser system with the Coulomb branch of the n equals 2 star theory on R3 times S1, or more precisely, if we take n equals 2 star theory and look at it on R3 times S1, that at low energies, the three-dimensional theory that we obtain is a three-dimensional sigma model into some hyperkiller manifold, and this hyperkiller manifold is exactly the phase space of these twisted elliptic Calogero-Moser systems that we define. So this is a lesson from Seiberg-Witten theory. Now we learn from this what the physical interpretation of the variables that appear in the twisted elliptic Calogero-Moser systems is. So the vertical variables, so if we let's split the position vectors Z, they belong to the complex plane. So we can split into a horizontal parts, let's say sigma I, and a vertical part, AI times tau. So when I say vertical is really in the tau direction and horizontal is in the horizontal direction. Now we can identify these vertical variables with the holonomies of the four-dimensional gauge fields along the S1, which appears in R3 times S1, whereas the horizontal variables are identified with the scalar fields due to the low energy photons on the Coulomb branch on R3 times S1. So this is how the correspondence between twisted elliptic Calogero-Moser systems and n equals 2 star theories work. So again, a couple of remarks. So n equals 2 star theories are obtained from n equals 4 super-Yang-Mills by turning on a bare mass for the adjoint hypermultiplet in n equals 2 language. So in some way, it's a mass deformation, but it's a milder mass deformation than that we need to do in order to go from n equals 4 super-Yang-Mills to n equals 1 star. Second remark is that n equals 2 star theories are in class S. The UV curve is a punctured torus. It's historically the first example of theories, n equals 2 theories in class S for which the UV curve is not a sphere, but rather a genus 1 surface. And therefore, twisted elliptic Calogero-Moser systems are actually specific cases of Hitchin integrable systems, and their phase space is a Hitchin moduli space on a punctured torus. And then third remark, n equals 1 star theories are generic n equals 1 mass deformations of n equals 4 super-Yang-Mills, as we saw, but we can also see them as generic mass deformations of n equals 2 star theories, which preserve n equals 1 supersymmetry. So as discussed in the first paper by Seiberg and Witten, when we start from a 4D n equals 2 gauge theory and deform it by turning on a bare mass for the adjoint chiral superfields belonging to the n equals 2 vector superfields, the consequence is that this mass deformation lifts the Coulomb branch, but the singular points corresponding to the singularities in the Coulomb branch. And therefore, if we start from n equals 2 star theories, for which we have the Seiberg-Witten solution, when we deform it further to n equals 1 star theory, then we find in a very natural way that the only thing that survives from the Coulomb branch corresponds to the vacua of n equals 1 star theories. And so in a nutshell, we obtain a correspondence between the isolated extrema of twisted elliptic Calogero-Moser systems coming from Seiberg-Witten theory and the massive vacua of n equals 1 star theories on R3 times S1. And that's why we're interested in the massive vacua of n equals 1 star theories on R3 times S1. Now, you can use, because again, the Seiberg-Witten theory, as well as the twisted elliptic Calogero-Moser systems are inherently non-perturbative. They provide a non-perturbative descriptions of n equals 2 star and n equals 1 star theories. You can use Calogero-Moser systems to study n equals 1 star theories at strong coupling. And this is a perspective that has been revived in a series of papers by Bourget and Trost in 2015. And in the heritage of which our paper also fits. Questions about this relation between Calogero-Moser systems and Seiberg-Witten systems? All right. So in that case, let me come back to the specific case of type A elliptic Calogero-Moser systems. So in type A, it turns out that the isolated extrema of these elliptic Calogero-Moser systems are known analytically. We have formula both for the position vector corresponding to these isolated extrema, as well as for the value of the potential of the Calogero-Moser system at these extrema, which comes from some modular properties of both the Calogero-Moser potential as well as these isolated extrema. So here in this figure, you can see the 4 isolated extrema that are usually given when people discuss the case of elliptic Calogero-Moser systems of type A2, namely those corresponding to the complex Lie algebra SL3. So that's when I want you to remember what we said about SU3 n equals 1 star theories on R3 times S1, for which we found 6 massive vacua. And hence I want to make this remark that this is weird in the sense that we find 4 diagrams corresponding to isolated extrema for SL3 Calogero Moser systems, whereas we have found 6 massive vacua for SU3 n equals 1 star theories on R3 times S1. And this is a bit odd because, again, we're expecting from physical insights a one-to-one correspondence between these isolated extrema of Calogero Moser systems and the massive vacua of the corresponding n equals 1 star theories. And this is from this that I want to transition to the last part of the talk, except if you have questions, of course. Okay, so let's now move to global variance of Calogero Moser systems. So as I was saying, we expect a natural bijection between isolated extrema of twisted elliptic Calogero Moser systems and massive vacua of n equals 1 star theories on R3 times S1. Now we have said that the number of massive vacua of n equals 1 star theories on R3 times S1 and even more, the way they arise from vacua in 4 dimensions depend on the global variance that we're considering. And therefore, we can conclude or guess that there must be a notion of global variance of twisted elliptic Calogero Moser systems as well, so that this matching can work. So that's the definition that is coming now. So just recall that a global variant L is a maximal sublattice in gamma weight times lambda weight, which is integral with respect to the Dirac-Schwinger-Zwanziger pairing. Or equivalently, we can see it as a Lagrangian subgroup in gamma weight modulo gamma root times lambda weight modulo lambda root. Now we can define the global variant L of the GC twisted elliptic Calogero Moser system to be a dynamical system of n particles in Cn living in the complex plane with a potential which is exactly the same as the potential we gave for twisted elliptic Calogero Moser system in the previous slides, but such that we impose a different periodicity condition. So remember that in the original definition of the twisted elliptic Calogero Moser systems I gave, we had horizontal periodicities by weights and vertical periodicities by co-weights. Here, we want to impose that 2 configurations are equivalent if and only if they differ by a shift, which is a horizontal shift by some weight and a vertical shift by some co-weight, such that the pair co-weight belongs to the maximal sublattice defining our global variant. And we have checked that this is a good definition, or at least we have provided evidence in favor of this definition in the sense that we find a perfect matching between the notion of global variance of twisted elliptic Calogero Moser systems and the Seiberg-Witten systems of global variance L of n equals 2 star theories. And we have checked that by considering isolated extrema of twisted elliptic Calogero Moser systems and showing that they satisfy all the properties that we are expecting for the massive vacua of the corresponding n equals 1 star theories, including, in particular, dualities. So let's consider, again, the SU3 twisted, so non-twisted, sorry, SU3 elliptic Calogero Moser system, except that now, instead of saying SU3 for the Lie algebra, I'm really considering the global variance SU3, like the gauge group, SU3 elliptic Calogero Moser system, or SL3 if you're considering the complexified gauge group. So in the first row of this figure, you have 4 configurations of points in the complex plane, which correspond to isolated extrema of the elliptic Calogero Moser system. And now, because of the definition of global variant that I just gave, the question is whether these extrema are equivalent or not. So in order to study that, let's consider first the 2 vacua A and, sorry, I'm saying vacua, I mean extrema. So let's consider extrema A and extrema B. We can see that extrema B can be obtained from extrema A by adding K2 times tau, where K2 is the co-weight of SU3 that we gave a couple of slides ago. So in that case, K2 is a fundamental co-weight, remember that the global variant SU3 contains all possible Wilson lines, but only the Hooft lines of 3 ality 0. So Chi2 is not the charge of a genuine Hooft line operator in the SU3 global variant of n equals 1 star theory. In other words, Chi2 0 does not belong to the global variant L, and therefore, by definition, we want to consider configuration A and configuration B as inequivalent. Now we can project these configurations to the torus. So that's the second line of the figure. And you can see that we obtain two different diagrams on the torus as well. And in the case of SU3, we want to consider these two configurations are inequivalent. So in terms of configurations of points on the torus, you see that the second configuration is obtained from the first by doing a shift in the vertical direction by 1/3 of the fundamental cell. And we could do it further. And that's exactly what we would obtain if we were to shift ZB further, again by Chi2 times tau, sorry. And so we find three configurations like that, which are obtained from the same diagram in the classical notion of Calogero Moser systems, which are the three diagrams in blue, which are shown in the last row of the figure here. However, if we were to try to shift by 3 times Chi2, then 3 times Chi2 is actually a co-root of the Lie algebra SL3, and therefore it belongs to the global variant, and this is also something that we can see on the torus here. So in this way, by using the definition of global variant that I told you in the previous slide, we find indeed not 4, but 6 isolated extrema for this global variant of elliptic Calogero Moser system, which is a good thing, right? That's what we wanted. Now let's compare SU3 and PSU3 0 elliptic Calogero Moser systems. So the SU3 case is the one we just described. So we have found 3 blue vacua, whereas we could naively think before that these 3 vacua were corresponding to a single isolated extrema of the elliptic Calogero Moser system. So the notion of global variant is actually refining our notion of isolated extrema. Whereas in the case of PSU3 node, the blue vacuum is unique, but instead it is the 4th vacuum on the first line, which becomes 3 isolated extrema, which are the isolated extrema 2, 3, and 4, appearing in the row corresponding to the PSU3 node elliptic Calogero Moser system. And now I want to remember the 2 tables that we had for the massive vacua of SU3 versus PSU3 n equals 1 star theories on R3 times S1. So remember again that in the partition 3 equals 3, in the SU3 case, we have found 3 massive vacua on R3 times S1. These 3 vacua can be identified with the 3 isolated extrema in the first row. Whereas in the case of PSU3, the partition 3 equals 3, we're giving rise to a single massive vacua on R3 times S1. And that's why we again find like a single blue extrema in the case of PSU3 0 as shown here. So in the other partition, we find 3 massive vacua for SU3, which are the 3 black diagrams in the first row. Whereas in the case of PSU3I, we find 5 vacua, which are the 5 isolated extrema that are shown on the second row. So that's a very good sign. Then, as I was saying, we can also consider dualities as a very powerful check of our proposal. So we have a natural action of PSL2Z on isolated extrema of twisted elliptic Calogero Moser systems, which basically come from modularity. So the particles, they live on something which is related to a torus. So we naturally have an action of PSL2Z. And that gives rise to a natural action of PSL2Z on pairs, global variant, and isolated extrema of L. And we have shown that this action coincides with that of the electric magnetic duality group on the massive vacua of n equals 1 star theories on R3 times S1. So the generator S of the modular group PSL2Z can be readily identified with the generator S of the duality group. However, there is a subtlety in identifying the action of T on the isolated extrema of twisted elliptic Calogero Moser system, which is related to the fact that when the dynamics reduces from the UV1 of n equals 1 star theories to that of pure Superring mills at intermediate energy scales, there can be emergent discrete R symmetries. And the Lie theoretic notion of embedding index for the unbroken gauge algebra in the UV gauge algebra plays an important role and relates the UV notion of T with the notion of T as it would be defined naturally for pure n=1 Superring mills. So typically, to fix ideas, consider the Lie algebra SU4. So we consider SU4 n=1 star theory and the partition 4 = 2 + 2. In this partition, the dynamics reduces at intermediate energy scales to that of pure n=1 SU2 Superring mills. And the embedding index of SU2 in SU4 corresponding to this partition is 2. And therefore, we find that the T, which is again the UV notion of T, and which is identified with the generator T of the modular group acting on elliptic Calogero Moser systems, is the square of the IR notion of T as it acts on the vacua of SU2, of pure SU2 Superring mills. So taking this subtlety into account, we can match the way S and T acts on the isolated extrema of Calogero Moser systems with the way we're expecting S and T to act on the vacua of n=1 star theories on R3 times S1, which is again providing a very non-trivial check of our proposal. So we can obtain in this way very nice duality diagrams. Typically for the global variant SU4 mod Z2 node, which is interesting because it is fixed by S and T, we have a duality diagram for only the isolated extrema of twisted elliptic Calogero Moser systems. And remember again that these diagrams are in one-to-one correspondence with the massive vacua of the corresponding n=1 star theory on R3 times S1, meaning that just by studying the action of PSL2Z on the on the elliptic Calogero Moser diagrams, we can infer the action of S and T on the corresponding vacua of the n=1 star theory. And in the case...
A question?
Yes.
So can you go back? So is this a divisor function that we see over here?
A divisor function. Is that the question?
Yeah.
Danton, can you remind me the definition of a divisor function?
It's the sum. So the various divisor functions, this would be the sum of all divisors of a given number. So for 4, it will be 1 + 2 + 4 = 7. Do you have 7 vacua? Yeah, 1 + 2 + 4.
Yes.
And,
So this is the case if you take the vacua column-wise.
say it again?
And this is the case if you take the vacua column-wise. But if you were considering the massive vacua on R3 times S1, then all of these 16 diagrams are massive vacua.
I see. And do you have a formula for the extension?
Yes.
The answer is yes. Okay.
At least we have a formula for counting those vacua on R3 times S1, yes.
And it is again a divisor function?
I see Antoine nodding, so we'll say yes. But
Yeah, then Antoine said yes. Okay.
It's a sum. It's always it's a sum of the divisors of n of some function of the divisor.
And it's still a multiplicative sequence.
And well, that was my other comment. I don't know, and I don't think we checked actually if it's a multiplicative one.
I see.
Because importantly now it depends on 2 integers. It just actually even on 3. It depends on n, and then on the one from symmetry you quotient it out, and then what is the discrete theta angle. So it's more complex. But then if you sum over some of those things, maybe you get back to some nice multiplicative function. We could look into that.
I see. Okay.
So yeah, thanks for the question. I'm gonna make a remark which is related to that. That if you take this diagram but column-wise, then each column corresponds to a vacuum in 4 dimensions. And we can learn about the vacua, the massive vacua of n equals 1 star theories in 4 dimensions by having this information of what the vacua on R3 times S1 are. For example, if you look at the first column, the fact that we have 2 rows is telling us that the corresponding vacuum in 4 dimensions actually has a Z2 discrete gauge symmetry. The fact that the second column displays 4 vacuum is telling us that the corresponding the corresponding vacuum in 4 dimensions displays a discrete gauge symmetry of order 4. And then by studying the way
Z2
quality
cos
acts,
2 or Z4?
yeah, so that's something that we can derive by looking at how duality acts on those diagrams.
Mhm.
In the case of type A, it's not particularly interesting because type A is extremely well behaved. And in particular, we know from Seiberg-Witten theory that there is nothing drastic happening as we increase the gauge coupling from a weakly coupled to strongly coupled regime. But in the case of SO5, which is the other example that we studied in our paper, for which we know much less in the strongly coupled region, we could really derive some information about the 4-dimensional vacua by studying the vacua of the theory on R3 times S1.
I see. Do you have also examples which are not simply laced that are like these diagrams that you draw?
Yes, I will. I have one slide, and we will come to it very soon.
Thank you.
Actually, no, I don't have I don't have these diagrams for SO5. I don't have it on this slide, but the diagrams look basically the same.
I see.
So it's also like a bunch of points on the torus. What changes is what can I say? The isolated extreme are not going to look as symmetric as in this type A case, but the diagrams they look basically the same.
I see.
It's still
Yeah, I'm just wondering which which divisor function one gets.
I think this is completely open. Like in type A, it's just my ignorance speaking. But in other types other than A, I discussed it recently with Jan Trost, and he was telling me that it would be interesting to find those counting functions.
Okay, I see. So it's not yet done.
So actually, just one compliment that I forgot to say when I first answered to your question about divisors. It is actually nice multiplicative because the total number of vacua for SUN or all global structures, it's actually a convolution of 2 very nice functions, and one is the sum of divisors, and the other one is called the Dedekind psi function. So if you convolve these two, that's the result. But actually, we couldn't.
And both of them are multiplicative.
Well, yeah, and but we could not. I think we could not formally derive. I mean, we haven't spent so much time, but so in the paper we put it as a conjecture, but it works for for all from 1 to 100. So
I see. Okay.
So it's a nice exercise to try to derive it.
No, it's definitely something that we would like to do as well, no? Like study better these counting functions and yeah.
I see.
Okay, so yeah, just want to give a more duality diagram. So the one here on this slide is very special because SU4 mod Z2 naught is a global variant which is fixed by SNT. It's isolated, like it's the connected component containing it in the duality diagram is just this guy. But then if we consider more general cases, for example, the case of SU3 theories for which the duality diagram is connected, then in that case, we find more complicated duality diagrams where the operations of S and T are both acting on the vacua of the theories as well as shuffling the global variance. So this gives rise to more complicated diagrams like these ones. And yeah. And so we can also wonder about the way these complicated duality diagrams split into orbits under SNT. And we have a list at the end of our paper for theories from SU2 to SU8. And some display very nice structures, which display some symmetries, but yeah, they remain for now mostly mysterious. Like we don't have a good explanation of why we see those symmetries. Like it seems to be something related to the modularity properties of subgroups of PSL2D, but I cannot say much about it. So that's now the slide about SO5 theories. So in the case of SO5 theories, there is an important novelty as compared to the type A cases, which is that there is a massive vacuum on R3 times S1, which comes from a gapless vacuum on R4, because the unbroken gauge group in that case, in this specific semi-classical vacuum of the n equals 1 star theory, is of the form O2, or maybe it's double cover pin 2, but it's a semi-direct product between an abelian group and a discrete gauge group, Z2. And when we compactify on a circle, if we give a vev to Z2, then it breaks the abelian factor of the unbroken gauge group. And this is a phenomenon that we don't see in type A. So in the case of SO5 theories, we have a specific vacuum, a specific isolated extremum that we see on the Calogero Moser's side, which is something very specific coming from the fact that we're considering the theory on R3 times S1, and which doesn't come from a gapped vacuum in 4 dimensions. So we can do the same game with SO5 theories, distinguishing spin 5, SO5 plus, and SO5 minus theories. And as I was briefly explaining, we can then derive for these theories, which are much less understood than type A theories, mostly because the Lie theory of SO5 is not as nicely behaved as the Lie theory for type A algebras. We can derive information about 4-dimensional vacua using our knowledge of the vacua of these theories on R3 times S1 that we derive from the elliptic Calogero-Moser systems. So typically, by deriving interesting information, I mean the pattern of condensing lines in the 4-dimensional vacua and the low energy effective theories that we see in the massive vacua of these SO5 n equals 1 star theories on R4. So I'm basically done. Let me briefly conclude. So we have derived and checked that there exists a good notion of twisted elliptic Calogero-Moser systems, which is associated to Lie groups rather than Lie algebras, or even more precisely global variants instead of Lie groups, which seems to be an interesting notion because usually Calogero-Moser systems are thought of as integrable systems associated to Lie algebras. And moreover, we can derive interesting and subtle physics from the study of these twisted elliptic Calogero-Moser systems. And there are many directions that we could be willing to explore in the future. Namely, a first is that for twisted elliptic Calogero-Moser systems of type D, it's known that there is a monodromy phenomenon when considering the isolated extrema of twisted elliptic Calogero-Moser systems, which is not understood. And this would be interesting to understand this monodromy phenomenon as well as the physics essence of this monodromy phenomenon. Then the notion of global variant of twisted elliptic Calogero-Moser system should also generalize to all other integrable systems corresponding to 4D n equals 2 theories via Seiberg-Witten theory. So there are some obvious generalizations, typically Toda chains, which correspond to pure n equals 2 super-Yang mills, but also spin twisted elliptic Calogero-Moser systems, which correspond to elliptic models or necklace quivers. And more generally, we could think of generalizing this notion to Hitchin systems, like for all theories in class S. There are some tools from a more mathematical literature that could be used in order to study this interesting notion, like this generalization of laminations that I was speaking of to higher integral laminations, for which we also have an intersection pairing, and coming with an action of the mapping class groups on these global variants. Okay, yeah, I want to stop now. Thanks.
All right, let's thank Valdo. Do we have questions? All right.
Yeah,
already
I
had
have one question.
Yeah, okay, there are more questions.
Can I ask you? Right, so many years ago, also I studied twist Calogero Moser systems, and this is there are two kinds of Calogero Moser system you can get in R4 cross S1, R3 cross S1. either you get it from, say, non-simplest group in 4D and then just compactify, or you can do the auto-automorphism twisting and then you compactify. And they generated two different type of theories. But interestingly enough, what we focused when we did was that when you twist the theory with auto-automorphism to R3 cross S1, I mean, in our naive analysis, number of vacuum doesn't change whether you twist it or not twist it. Now you put the element of this higher form symmetries. So I'm just wondering whether one can ask the same question, whether number of vector changes or whether they have, because if you go to large radius, then you are coming back to the original theory. So there should be a certain sense of invariance. And also in that calculation, the potential when you write down, every numerical factor has to be precise, otherwise you don't get the right number of vectors, even for just total twisted total models. Never mind. So there's a very nice relation between the root, co-root, dual Cox number, or co-max, that sort of things. So
I see. Thanks for the comment. Yeah, it seems like a very interesting direction.
What was your motivation back then, Kim Young?
Well, right. So this is a beautiful work people done in Equal One, but we are learning stage, and because I worked on magnetic monopoles and instantons, we see how instanton and monopole effect appears when you twist it. And naturally, we are learning and writing it. I mean, we have to do something, and naturally, we are twisting. And that led to me to this direction. And recently, we again twisted the 6D Tucumajara theory on a circle. Then you get a 5D non-simplest group, but not Keck-Smoot algebras. There, we are looking at the, I think I gave a talk maybe here many years ago, where we are looking at the vacuum, the twisted omega deformed elliptic genus, which is related to black hole entropy. And the large momentum limit, or Cardi limit, is the limit where you are looking at short distance physics because you are looking at high momentums. And then your physics should be invariant whether you are twisting or untwisting it, some sense. Degrees of freedom hasn't been lost because you just shifted the momentums. And we got a black hole entropy because we are looking at T2 cross R4 with omega deformed partition function. And the black hole entropy is a complicated function of the charges, but one thing is that dual Cox-Sector number times dimensional group times momentum appears. Now, twisting changes the dual Cox-Sector number and moment dimension, of course, but the momentum changes only, number of momentum should be more or less same. Change of radius is there, so there's identity appearing very naturally. So, for example, start with 6 and 5 rains, and then G2 automorphism twisting to 5D. Then instead of you get it's not Yang theory, so you don't get the twisted Keck-Smoot algebra, which is USB6. You get it's Langland dual SO7. And if you look at the dual Cox-Sector number times dimensional group for, say, SU6, that's 6 times 35. SU6 is 6 times 35 is a dual Cox-Sector number times dimensional group. Then you divide by order of the automorphism, which is 3 times 35. Now let's look at SO7, whose dual Cox-Sector number is 5. Dimension is 21. So 5 times 21 is 3 times 35. So it's invariant. And we find that invariance to the order twisting. So, I mean, 60 and 5D n equal to Yang theory as, non-simplest group arise from twisting of 60 ADE series. So there's identity. And there's one more subtlety, but So another thing is when you say SO5 minus is self-dual,
Yes.
or SO3 minus is self-dual, it's not really, that's not, I don't think it's the right description. I think it's, I don't know why there was some jump in stories. A long time ago, it was called O3 minus tilde, and theory living on it was SP theory with discrete setup in, say, I mean, continuous setup in 2 pi because SP theory has a range 4 pi, so that you have a SP thinking diagram which is long root, but its magnetic charge is short root, but it has electric charge, which is half of the W boson charge. So you need 2 of them, making long root. That's why it's self-dual. So it's SP theory is self-dual, not SO5 minus. But if you go to SO7 minus, there is no such a thing. So I think this is misnamed by some later on by this group of people, even though I don't know why. And you can read about that also, my old paper where we are looking at plane diagrams and so on.
Okay, I'm not sure I understood. Like you're speaking of
O3 minus,
orientifolds,
O5 minus self-dual on the S-duality.
but this is for orientifolds, right? Not
Yeah, but I'm saying that if you go to O7 minus, it's not true. So because O3 and O5 is SP2 and SP4, that's why they have. But if you go to O7 minus, there is no O7 minus. But I'm saying SPN, there is a generalization. That's what I'm saying.
Are you like in my case there was like for example the SO5 minus theory.
Oh, that's okay. SO5 is SP4, so it doesn't matter. It's identical. But I'm saying that if you go to SO7, it doesn't work. I'm saying you have to go to USP6. And then,
so we agree that SO5 minus is because I thought you said that.
yeah, that's okay. That's okay. SO3 minus, SO5 minus is okay. But when you go to SO7 minus, it's not true.
Yeah.
USP6.
No,
And
that's
so
why. That's why
so
it was
people
not to generalize to SO7 minus.
no.
Yeah.
It's a USP6 minus. USP6 still or whatever.
Yeah,
And
then
that's
I agree.
all right.
Good.
Thank you.
Do we have more questions for Valdo?
I just wanted to say regarding to the last comment that in the case where for instance, SO7 and USP6, you would still have a duality, and it would the S action would send extrema of the SO7 theory to extrema of the USP6 and conversely. So you would also have a web of connected things.
Of course. Right, but I'm saying that SP6, you can shift the theta by 2 pi, then it's invariant on the S duality by itself. That's what I'm saying.
Sure. Yes.
Yeah, it's not S, right? So there's no SO5, SO7 minus kind of thing.
No, sure. Yeah.
SP6.
The only thing,
But there is also an SO7 minus, which is
Really? But it's self-dual on the S transform?
which is self-dual, yes.
SO7 minus? But it doesn't have orientifold description.
I think it's at least I don't see the connection with orientifolds. The connection between this plus minus and O plus O minus in terms of orientifold, I don't see this connection. But in terms of global forms of the gauge theory, there is always, for any odd n, there is SON plus and SON minus. I think for any n, you can take SO13 plus or minus. We can discuss later if you want.
I'm not sure that you can get the global variant from the orientifold description of your gauge theory.
Maybe let's see if there are any pressing questions for Valdo. Any takers? If not, I would say let's thank Valdo again.
Thank you.
And let's go off the record, and you can discuss these things, without it being on YouTube.
Okay.